So this lecture begins the topic of binary codes, and the aim will be to set up a system whereby we can send a message and a check part in binary so that the two parts together enable us to correct a simple error in the message. And we'll be working, as I mentioned before, with just zeros and ones. So with our alphabet, I'm going to call it B. It just consists of 0 and 1, but very soon we're going to think of this as a field with two elements. So some people might write this Z2 or F2, although it's really a quotient ring. It's really Z divided by the even integer, Z over 2Z. In particular, we can add elements in the usual way, mod 2. So 1 plus 1 is equal to 0 in this system, and we can multiply 0 and 1 together in the obvious way. Now we'll be working effectively with vectors with various components of zeros and ones. So we'll be working with elements in the space Bn, which is just the product of B with itself n times, just as we work in Rn, except that Bn is in fact a vector space. We can use all the tools from vector space theory, but it's a finite vector space. In fact, each component, we've got a vector of length n, each component can be 0 or 1, so that gives 2 to the power n elements. So always remember, b to the n has 2 to the n elements. So 1, 2, 4, 8, 16, and so on, depending on n. So, and also I'll write vectors rather than conventionally with parentheses and commas and so on. I'll just write a vector as a string of elements of the alphabet. So it might be, if we're working in B5, I might write sort of 0, 1, 0, 1, 1. That is an element of B5. I'm really thinking of it as a vector with those components. So in particular, I can add two vectors together. So here is another element of B5. And if I add those two vectors together, remember 1 plus 1 is 0. So I just get 1, 0, 0, 0, 1. So that's how I add vectors in B5. Now we can compare two vectors in Bn together, and the number of bits by which they differ is called the Hamming distance between them. So perhaps I shouldn't have changed page so quickly. If we go back to this example, you see I gave you two vectors above the line, and they differ in two positions, the first position and the last position. So the Hamming distance between these two vectors is actually equal to 2. So we would write distance between, if I call the first vector v1, or v1, but I need to really underline that if this were typed, it would be in boldface to make it clear I'm not talking about individual numbers here, I'm talking about vectors. And the distance between these two is equal to 2, the Hamming distance. I'll often use symbols like A, B, C, so I might, under boldface, so I might call this A, this first vector, and the second one B. So it would be distance between A and B would be equal to 2 in that case. So moving back, there's the definition. So it's a very simple notion, it's a very simple concept. You just compare the two vectors, although as I said, it's easy to do this more easily. You've got to really put one on top of the other, particularly if they're long vectors. And then what is a binary code? Well, it's very, very simple, the definition. It's just a subset of Bn, B to the n. So we're just distinguishing certain elements we're distinguishing certain vectors. We've got a total of 2 to the n vectors. We're just distinguishing some of them. And the setup is very much like that of, say, bank account numbers. So we saw in the first lecture that we have lots of sort of potential numbers we could use, but only some of them will be valid because they have to satisfy some modulus condition. In the case of an IBAN, it was modulo 97. So the chances are, if you work out the remainder, it's not going to satisfy that. So we're only looking at, roughly speaking, 1/100th of all the numbers possible. So our code in that case consists of a subspace, which is roughly 100th, or subset, I should say, which is roughly 100th of all the possible numbers available. And the code is called linear if actually this is a subspace. We're now back to linear codes. The bank account numbers obviously is in the decimal system. The code will only be dealing with binary codes. The code is linear if it's a subspace of Bn rather than just a subset. And what that means in practice is that, you see, normally for a subspace you have to check addition and scalar multiplication, but there's no scalar multiplication to check. So you only have to check that if you have two elements of the code, capital C, when you take their sum, so A and B in the code, the condition for subspace is that if A and B are in the code, then their sum has to be in the code. That's the only thing you have to check. Now, in particular, if you sum a vector with itself, you get the 0 vector, because 2a, if you like, is like 0 times a, or you're adding all the identical components together. So each component, when you take the sum, is 0. So in particular, the 0 vector has to belong to C, just as the 0 vector always has to belong to a subspace. So I don't have to say that as an extra condition. That just follows from this condition which I've written here. That's the condition to have a subspace. Now, the other thing which is important to say straight away is that what we're trying to do is the idea is we're going to transmit only the code words. So if we want to send a message, it should be one of these code words. Just like if we want to send a bank account number to transfer money abroad, it has to be validated. It has to be one of our validated numbers. That's like saying it has to be a code word. So if we get a number, if we receive a number that's not a code word, we want to try and guess what was intended. And the point is that we look at all the possible code words that differ by as little as possible from the number we receive. And we assume that what was intended was the code word closest to the word we receive. So that's the minimum distance principle. And we'll always use that in our discussions and results. So if we get an invalid word, that means a word that's not in capital C, then we're looking for an element of capital C for capital, say, Y, for which the Hamming distance between X and Y is as small as possible. That's the minimum distance, sometimes called the nearest neighbour principle. Now, so we're now beginning to understand what we need to do to design an effective code. We want to make sure that we have this distinguished set of code words which are placed amongst all the words, all the elements of Bn. We want to make sure that we don't have two code words that are close together, because if we have two code words that are close together, we can easily find a word which is not a code word, but for which we don't know which code word is closest to it. So we want to try and space out, given the sizes of these things we've decided, we want to try and space out the code words as much as possible in the vector space Bn, if we're using n messages of length n, total length n. So for this purpose, we define the minimum distance of a binary code. It's simply the minimum of the distances between the code words. Remember, not all the words are code words, only some of them. So we can define delta to be the minimum, the least distance between two code words, two distinguished words. Now, here's the key point. So here's a lemma from the lecture notes. So the case really, the first case which is of any use is that in which delta is at least 3. So in general, let's suppose that delta is at least as big as the odd number 2e plus 1 for some value of e, which typically will be 1 or 2 or 3, depending how large n is. So suppose that this minimum distance is at least 2e plus 1. And suppose we have an arbitrary word which is within a distance of 2 code words, within a distance e, a Hamming distance e of 2 code words. That means we can just change e elements of x and get y, and e other elements of x and get y primed. Suppose that's the situation. The idea being that maybe we transmitted y, but because of errors of transmission along the way, we actually receive x, which differs from y in e positions. So the code word has been corrupted, or the message has been corrupted in transmission. But suppose we have 2 code words that have this property. Then because this Hamming business, the Hamming distance, is actually a distance in the sense of metric spaces, it satisfies the triangle inequality. That's quite easy to prove. I'm not going to do it today. But it satisfies the triangle inequality. So if we look at the distance between our 2 code words, the Hamming distance between them, that's going to be less than or equal to we can think of sort of having the x here, and we have our 2 code words, which it's within a distance e of. We have y and y primed. And so by the triangle inequality, we can say the distance from y to y primed is less than or equal to the sum of the other 2 sides of the triangle. But by assumption, that's less than or equal to 2e, because we're getting x from y by just changing e bits, similarly from y prime. So the distance of y to y primed is less than or equal, is strictly less than delta. It's less than or equal to 2e, which is strictly less than delta. Therefore, y has to equal y primed. I didn't actually exclude that originally. It could have been the same. I didn't say they weren't the same code word. So what this shows you is you can't find 2 distinct code words with this property, if we know that delta is at least 2e plus 1. So what that means is that if we have a binary code with this lower bound on the minimum distance, we are able to correct e errors using the minimum distance principle, because we cannot find 2 different code words which are within e of a word x. So in many of the examples we'll be doing e is 1, so we want delta to be at least 3, or if delta is at least 3, we're in business. And a second result, which I just want to state and not prove, is that if we have any code, it doesn't have to be linear. Now, these lemmas don't require code to be linear. In the sense they're simpler. We're not using linearity. We're not using the subspace property. We have any binary code for which delta is at least 2e plus 1, then because we're sort of separating the code words, we can't get 2 code words too close together. It means that we have to have enough space around the code words. And what this means is that depending on the value of e, it means for each code word, we have we need a certain space around it. So if we're just correcting one error, then we just need the code word itself, and we can change it in in n ways by just changing one bit. If we want to change 2 bits, we can do that in n choose 2 ways, and so on. If we want to go up to changing n bits, we have to include n choose e. So if we take the sum of all these things, if e is 1, we don't need this part here. If we take the sum of those things for each code word, we've got to fit that in as distinct elements in our vector space with 2 to the n elements. So that's why we have this lemma 2 that's valid. So this is giving us some sort of explaining the difficulty really in finding a code that corrects a certain number of errors. Now I want to give you the first example of a binary code, and it will actually be linear. I'm not going to waste time with example. You should be able to recognize when a code is linear. First of all, it's got to include the 0 vector, and it must be the case that when you add any 2 code words, you get a code word. But assuming we can understand that, I may as well concentrate on examples of linear codes. So here is, I'm going to define this in a way that will relate to the theory later on. Here is a linear code, and I'm going to do, well, I haven't told you what it is yet, and I'm about to tell you. First of all, I take this binary matrix called E stands for encode, and it has 2 columns. So it's a matrix, I would write it like this to be honest, so it's a matrix of size 5 by 2. It has 5 rows and 2 columns. So I say that it's an element of B5, 2. That's the notation I use even for real value matrices. I just would say R5, 2, 5 rows, 2 columns. It's also special because the top square is the identity, and that makes it useful to do the calculations. So I also want to remind you that when you have a matrix like this, you can use it to define a linear transformation. Now, my convention will always be that matrices act, when you convert them into linear transformations, you make them work on column vectors. They act on column vectors. That's related to the fact that when we talk about functions, we always normally put the function on the left of the variable. So I want to put the linear transformation of the matrix on the left. So that's why I make matrices act on column vectors. Not everyone does. So if we do that, it means that the column vectors we're acting on have to have size 2, because when we do matrix multiplication, we take each row and sort of move it around by 90 degrees and make it act on a column vector. So the column vectors would have size 2, so we're talking about an element of the vector space B2, and yet because E has 5 rows, we'll end up with a vector of size 5. Of course, the classic example, if we take a matrix and we act on the column vector 1, 0, we know very well that we get the first column. That will always be true. So in this case, we get 1, 0, 1, 1, 0, which I denote by C1. It's the first column underlined or in boldface. It's the first column vector of the matrix. If you act on 0, 1, you get the second column. That much we know. By the way, although these are column vectors, they're also going to represent words. So we have to be ready to convert this into a word. So as a word, it looks like that. Whereas the second column as a word looks like this: 0, 1, 0, 0. No, I've got that wrong. 0, 1, 0, 1, 1. 0, 1, 0, 1, 1. Now I can even add up the 2 columns. That would give me 1, 1, 1, 0, 1. And what I want to do is I want to define my code to be the image of E. So before I type that out, let me just say, what is the image of E? Well, the image of E is generated by the columns of, this is true for any linear transformation. If the matrix represents a linear transformation, the image of the transformation is generated by essentially the columns of the matrix. But here, generated by just means we can only take linear combinations with 0 and 1. So we only get 4 elements. The image has dimension 2, so we get 4 elements, 2 to the 2. And the 4 elements are the 3 I've written down together with the 0 vector. So these words are going to be our code. And this really just corresponds to the image of the matrix, or the linear transformation corresponding to the matrix B, generated by its columns. But you have to be ready to exchange columns with words. I'll never write the words with parentheses, so there shouldn't be any confusion. So let me say that formally. So we're defining our code. Remember, code just has to be a subset, in this case of B5, and it's going to be the image of E. So it's the span of the 2 columns of E, that is these 4 elements, just all possible linear combinations of the columns, but there aren't many choices. It's just 0 or 1 times the first column plus 0 or 1 times the second column, and that just gives us these four choices. Okay, so more or less saying the same thing, I'm saying that each element of the code is in the image of E. So it's E of some vector. Well, what is E of some vector? Well, remember that this bit at the top of E is the identity matrix. So when we apply E to a vector V, so V is a vector with 2 components. It's a column vector of height 2. What shall I call its components? Maybe just X and Y for the moment. So V is a vector in B2. And when we apply E to this, it's clear from the form of E that we've got to end up with a vector of height 5. And the first 2 components will just be V itself, because we've got the identity map. We can act by blocks. We've got the identity mapping acting. So that will just give us V. And then if we call this matrix A, this 3 by 2 matrix I called A, we just get, in the last 3 components, we just get AV. So that explains why we have here AV. So any element of our code has this form. And if you go back to the elements that I wrote out before, you'll see that indeed the first 2 elements, here it's written out horizontally, but the first 2 elements are indeed either it's 0, 0, 0, 0, 1, 0, 0, 1 or 1, 1. That corresponded to V. Okay, and we have that because the top part of E is the identity. Now, the utility of this is that we can think that the message we want to send is really the vector V. We want to just send these 2 bits corresponding to V. So there are 4 of them. Either we have 0, 0, 1, 0, 0, 1, or 1, 1. These are the 4 possibilities here. Now, in this example, you can think of this as telling a robot which direction to move in. Either it moves upwards, obviously 1, 0 makes sense to use 1, 0 for that, or north. South would be 0, 1. It's not clear what east or west should be, but let's use 0, 0 for west and 1, 1 for east. So that means move 1 step in those respective directions. That's the message we want to send. Obviously, we're going to send it repeatedly, but that's the message we might want to send to a robot. But we might be worried that this message gets changed. So 1, 1 could easily be changed to 0, 1. So we need more information to confirm that we really mean 1, 1. That's what we mean. So that extra information is given by this part of the message that's sent. So we can think of the rest of the vectors. Remember, there were 5 components. The remaining 3 components, they represent the check part, which will confirm the message. They'll allow us to correct an error. So if we receive one of these vectors in B5 that's not a code word, we can work out what message was intended, which of these 4 messages was intended. So in this situation, the check part is actually bigger than the message itself, but we need that in order to correct, because this is not a very efficient code. It's quite a difficult problem to find efficient codes, but because this is not very efficient, we need a message that's, the check part is actually bigger than the original message, not like for our IBAN, in which we had 26 characters and 2 check digits. But that was serving a different purpose. It wasn't correcting errors, it was just detecting. Okay, so that's the sort of basic example, and I want to explain this example graphically. Now, don't be frightened by this graph. You'll never have to draw graphs like this. But I just want to give you an idea, because you've probably never worked before with these finite dimensional vector spaces. But you see, in this example, we're talking about, in the example I was just doing, and that's what I'm talking about, we're talking about B5. And B5, so our words are in B5. The words we're going to send, which include the 2 bits of the directional message plus 3 check bits, those words belong to B5, whether you think of them as column vectors or strings of 0 and 1s written horizontally. So here I've written them as strings, and there are 32 of them. 2 to the 5 is 32. The size of b to the 5, remember, it's 2 to the 5, which is of course 32. And here there are 32 they're all written out here. You can find any string, any combination of 0s and 1s you care to think up, except unfortunately you don't see there are 2 in the middle actually that coincide in this picture. This is simply just a 5-dimensional hypercube. It's just a 5-dimensional version of the cube graph. The edges here are drawn when two words just differ by distance 1. So that means only 1 bit has been changed. So for example, along the top, we've only changed the first digit to shift from a 0 to a 1. We don't really need the edges, but it just for once it sort of shows you, I think, what's going on. So the Hamming distance would be corresponding to a shortest path between 2 of these words. Now, I just wanted to focus on one code word remember I'm still doing our example. So in our example, we have this code word, actually it's the second code word, which is this one here. And I wanted to sort of show, first of all, where that is on the picture. So if you look carefully, you'll find it's actually here. So I've just obscured it, which was the wrong thing to do. But I'm going to obscure it, but it's here, 0, 1, 0, 1, 1. So it's there, I'm going to put a dot there. And then what I can identify are the words I get to by just changing 1 bit. So I've listed them here. There are 5 choices, of course, depending which bit you change. If you change the first bit, you get 1, 1, 0, 1, 1. And you can find these points somewhere on this graph. They're going to be just connected by a single edge. You have to be a bit careful because the graph is rather complicated. So in particular, you can get 0, 1, 1, 1, 1. And you can get, so we can get this, 0, 0, 0, 1, 1. That should be in our list. We can get this point, 0, 1, 0, 0, 1. We can get this point, 1, 1, 0, 1, 1. And that just leaves actually a point which is obscured, which is the center, one of the 2 center vertices, whichever one I've left out. Okay, 0, 0, 1, maybe 0, 1, 0, 1, 0. So this is the code word, and I've highlighted the 5 other words which correspond to these 5 vertices which are a Hamming distance 1 from the code word. So the idea is this: if we receive a message which is one of these 5 vertices around, the idea is we should be able to say for certainty that what was intended was the code word. Okay, now that's going to work because the distance in this setup, as we'll see next time, the distance between any 2 of our code words is at least 3. What we can check. I mean, actually, I'm just using lemma 1. I don't need to refer to next time. If you look at our code words, our list of code words, which is quite a way back, the distance between any 2 of them is at least 3. In fact, the distance between 2 of them is actually 4. The distance between C1 and C2 is actually 4, but we only need the distance to be at least 3. So therefore, this code will correct one error. And what that means is if we're in one of these 5 vertices around the outside, we must be closest to this code word in the middle and no other code word. And I've prepared, you can think of this as a sort of spider. You have the code word in the center, which is the body of the spider, and you have these legs. This is just for correcting one error. Unfortunately, there's 6, not 8 legs. Sorry, 5 legs, because we're working in B5. We'd have to work in B8 to get 8 legs. But you can imagine that we've got 3 other code words to fit into this picture. What I'm telling you is that if you put those 3 other spiders in this picture, they will not touch each other. They'll be separated out. Okay, and I've actually done that to convince you that that works. There are the 4 code words corresponding to the central vertices in these 4 coloured spiders, if you like. Remember, the vertex in the centre is really 2 vertices. So if you look very carefully, you see there's no intersection of vertices. These are disjoint. So how many vertices do we have altogether here? Well, each code, we've got 4 code words, and we can change 1 bit in each code word. That gives 5. So that gives a total of, for each code word, we've got 6. The spider has 6 vertices, a body and the legs. So we have 4 times 6, which is 24. I've highlighted here 24 vertices, and no two are the same. And it's that fact that allows us to correct one error, because whatever we receive, and we're always going to receive, if we only have 1 error in the message, we're only going to receive one of these coloured vertices. There are 6 which are not coloured, but they can't be received because they differ from our intended message or code word by more than 1 bit. But if we just change one of our code words by 1 bit, we'll end up with one of these coloured vertices. None of them, the different colours don't intersect, so we know for certain, without ambiguity, what code word was intended. It would either be the green one, which corresponded to column 2, or the blue one, which corresponded actually to 0, 0, 0, 0, the 0 vector. That was very easy to put on this graph because I was just looking for the vertices which just had a single 1 and the rest zeros. Or the red spider corresponds to the first column of our matrix, and the black spider corresponds to C1 plus C2. So those are the 4 code words and all the vertices within Hamming distance 1 of the code word. And this picture also explains lemma 2 in the special case in which E is 1, because we have the number of code words, which here is 4, times the code word itself plus everything you can get by changing 1 bit. So that gives a total of 6. So 6 times 4 is 24. That is less than or equal to 32. That has to be the case. That inequality in itself wouldn't guarantee the existence of a code, but this picture does, in theory, tell you that such a code exists. But In practice, you don't need the picture. You can just check it from looking at the bits and checking. All we have to check in this example is that the minimum distance between our code words is at least 3. And we know then from the theory, just that I've done today, that from basically the triangle inequality, that setup will correct one error.